Hello everyone and welcome back to our channel. Today, we are going to take you back in time to 1909, when an American astronomer named Robert Wood published a report on his new experimental telescope that some of his contemporaries straight up called a joke. But it was a telescope that didn't use a big lens to collect light or the standard glassy mirror. Instead, when the universe's light rays came streaming in, the thing that they encountered was a pool of liquid mercury. Robert Wood had designed a liquid mirror telescope, and while he quickly abandoned the idea, modern astronomers have returned to the design as a legitimate, albeit quirky addition to their ground telescope fleet. In this video, we'll be exploring the history of the liquid mirror telescope, how it works, and the advantages and limitations of this fascinating technology. So let's begin. To study the cosmos, astronomers capture light. Sounds simple enough, but those light rays have to be captured in just the right way, so the resulting image comes out clear. Ever since Isaac Newton came along in the 17th century, the most popular way to do this has been with curved mirrors, but not just any curve. It's a specific shape called a parabola, which focuses all the light rays that come in at any angle onto a single point. As for the size, bigger is better. The bigger the mirror, the more light it can capture, and the more detail we can make out in the images it produces. Over the centuries, telescope mirrors started getting too big, not for the science, but for engineering. Large mirrors are difficult to transport. They are fragile, incredibly expensive, and after you make them, you have to continue polishing them throughout their lives, so they can keep doing their job. That's why super large telescopes often make their mirrors in segments, and then piece them together like a jigsaw puzzle. In the mid-1800s, a few astronomers considered a different way to collect light without breaking the bank. Instead of freezing the shape of a parabola into a solid piece of glass or shiny metal, a liquid mirror telescope, LMT, would create its curve with the power of physics. All you need to do is fill a shallow container with the liquid of your choice and spin it. As the container spins, the centripetal force will force the edge of the liquid to flow up as it presses against the walls of the container. Meanwhile, the center of the pool is pulled downward by gravity. Boom, it's a parabola. By changing the speed of rotation, you can adjust how extreme the curve of that parabola is, and how far away all the light rays will meet up. The faster it spins, the more deeply curved you could make your telescope's reflector. The first of many challenges in building an LMT was finding the right liquid. Water reflects sunlight, but not well enough for astronomers to study the night sky. So the first known LMT experiments used an even more reflective liquid, mercury. Even though scientists already knew that hanging out around it was bad for your health, in 1875, down at the Dunedin Observatory in New Zealand, Henry Skye built a proof-of-concept liquid mirror that was 35 centimeters wide. He produced test images in the laboratory but never used it for actual observations. Robert Wood, however, aimed bigger, 50 centimeters or half a meter, and it worked. Unlike Skye before him, Wood actually used his LMT to observe the night sky. He was able to clearly see the Milky Way and track a few individual stars as they passed directly overhead. One of the main advantages of LMTs is their low cost compared to traditional large telescopes. For example, in the 1980s, the University of British Columbia's astrophysics group led by Airman No Borer proposed building a liquid mirror telescope on the summit of Mount Cobo in British Columbia. The mirror would be 6 meters in diameter, and the total cost of the project was estimated at just over $1 million Canadian dollars, a fraction of the cost of traditional telescopes of comparable size. In addition to their low cost, LMTs have other advantages over traditional telescopes. For one, they are easier to transport, as the mirror can be shipped in a flat container and filled with liquid at the observing site. Additionally, because the mirror is not a solid piece of glass or metal, it is not subject to the same thermal expansion and contraction that can cause distortions in traditional mirrors. This makes LMTs more stable and less susceptible to thermal effects. Despite these advantages, there are still some challenges associated with building and operating LMTs. One of the biggest is the choice of liquid. Mercury is highly reflective, but it is also toxic and can be dangerous to handle. Other liquids, such as gallium or a mixture of gallium and indium, have been used in place of mercury, but they have lower reflectivity and require higher rotation speeds to achieve the same parabolic shape. Another challenge is the need for a stable platform to rotate the mirror. Even small disturbance in the rotation can introduce distortions into the image, so the rotation mechanism must be carefully designed and maintained. Finally, because LMTs can only point straight up, they are not suitable for all types of observations. They are best suited for studying objects that are close to the zenith, such as stars and galaxies directly overhead. Despite these challenges, LMTs have proven to be a valuable tool for astronomers. They are currently being used to study a wide range of astronomical phenomena, from exoplanets and gravitational waves to the large-scale structure of the universe. As technology improves and new liquids are developed, it is likely that LMTs will continue to play an important role in ground-based astronomy. The liquid mirror telescope may have been dismissed as a joke by some of Robert Wood's contemporaries, but today it is a valuable tool in the astronomer's arsenal. By using the power of physics to create a parabolic mirror, LMTs offer a low-cost, lightweight alternative to traditional telescopes. While they are not suitable for all types of observations, they have proven to be a valuable tool for studying objects near the zenith, and they are likely to continue to play an important role in ground-based astronomy for years to come. If you're interested in learning more about other planets and humans' progress in finding alternate life, subscribe to our channel. We create content about outer space and talk about innovations in science. If you enjoy this content, leave a comment below and share this video with your friends.